Welcome back to the Machine Design Engineer YouTube channel. In today's video, you will learn how the linear force is converted into a rotational torque, why ball screw efficiency affect motor torque, and how to calculate theoretical torque. We will also learn how to calculate a actual torque, how to apply practical design safety factor, and finally the torque value that will be used for servo motor selection. This video is the second part of servo motor selection. If you don't watch first video, click on I button and watch it first. Let's get a quick recap for previously calculated values. And you know our moving mass is 15 kg, maximum speed is 300 mm per second, and ball screw lead is 10 mm. We have selected in a previous video. And ball screw efficiency. As per manufacturer's catalog, we must have to be select a ball screw efficiency 80 to 90%. We are considering 90% efficiency for our calculations. Our maximum axial load is 192 Newton and servo motor speed is 1800 rpm. In the previous video, we have calculated that the maximum axial force acting our laser cutting machine Z axis is 192 Newton. And we determined that the ball screw must rotate at a speed 1800 rpm to achieve a linear speed of 300 mm per second. Now we will calculate the torque required to rotate the ball screw. This torque is the minimum torque and the servo motor must produce before we consider inertia and dynamic effects. First understand what is torque. Force produces linear motion. Torque produces rotary motion. The servo motor rotates the ball screw and the ball screw convert rotational motion into a linear motion. And to calculate torque, we must know the ball screw efficiency. And as per manufacturer's catalog, we are considering a 80 to 90% and we are considering 90% efficiency for our design calculations. And we know the ball screw having a recirculating mechanism, so that the ball screw having a high efficiency because it uses a recirculating ball mechanism instead of sliding contact. There is a two types of ball screw. First is rolled ball screw. Rolled ball screw is having efficiency 80 to 90%. And second type is ground ball screw. And ground ball screw is having efficiency 90 to 95%. And for our design, we have selected a ground ball screw which is having efficiency 90%. And this efficiency we are not assuming. This value comes from manufacturer's catalog. You can see here is the 90% efficiency. First calculate driving torque. And to calculate the driving torque, we know the formula. Torque is equal to force multiplied by lead divided by 2 pi multiplied by n, where tau is the driving torque, F is equal to force means axial force, L is ball screw lead, in our case is 10 mm, N means ball screw efficiency which is 90% in our case. Before putting the values in the formula, convert lead into a meter. Our lead is 10 mm. If we convert into a meter, so we get 0.01 meter. Put the values in the formula. So we get torque is equal to 192 multiplied by 0.01 divided by 2 pi multiplied by 90% efficiency means 0.90. So we get torque 0.34 Newton meter. This means the servo motor must produce 0.34 Newton meter torque just to overcome the axial force and rotate the ball screw. Now the most important step is apply safety factor. Machines do not always operate under library conditions. Variation in lubrication, manufacturing tolerances, wear and transient loads means we should include a design margin. And for lightweight industrial Z-axis, the safety factor is normally considered 1.5 times. After applying safety factor, our torque becomes 0.34 multiplied by 1.5. So we get a torque 0.51 Newton meter. And the most important thing is that the safety factor 1.5 is design choice, is not a physical constant. So now we have a axial force 192 Newton, ball screw lead is 10 mm and ball screw efficiency is 90%. Our calculated torque is 0.34 Newton meter. After applying safety factor, our torque becomes a 0.51 Newton meter. Now we have determined a design torque, which is 0.51 Newton meter. Now start with the inertia calculations. Why inertia is important? Because the most of the beginner design engineers select a servo motor based on only torque, but the industrial system selected based on the both, means inertia and torque, and the servo motor must produce enough torque to move a load. In our case, a laser cutting machine head, moving plate and ball nut weight, and also accelerate the all rotating components and also maintain a stable control without vibrations and overshoot. That's why inertia calculations is essential. Let's start inertia calculations. Before starting calculations, let's understand what is inertia. Mass resists the linear acceleration and moment of inertia resists rotational acceleration. Example, pushing a shopping cart is mass and rotating a flywheel is inertia. Now understand the components contributing to inertia. And the components is servo motor, coupling, ball screw and moving plate. The servo motor accelerates motor rotor, coupling, ball screw and reflected moving load. Let's start from ball screw inertia calculation. Instead of guessing any values, start calculating from geometry. We know volume V is equal to pi r square multiplied by L, and mass means M is equal to rho into V, where rho is density, and we know our ball screw material is stainless steel and density of steel is 7850 kg per meter cube, and we know our actual support distance is 288 mm and machining extension is near about 40 mm. So our total screw length is 328 mm. Converted into a meter, so it becomes 0.328 meter. Now determine the ball screw diameter, and we know we have previously selected a ball screw in 1610 ball screw. So our diameter is 16 and radius is 8 mm. So convert this 8 mm radius into a meter, so it becomes 0.008 meter. So now calculate the volume of ball screw. And we know the formula V is equal to pi r square multiplied by L. Substitute the values in the formula. So we get volume 6.59 multiplied by 10 raised to minus 5 meter cube. Now calculate the mass of ball screw. Our density is, and our ball screw material is stainless steel. So our density is 7850 kg per meter cube. And to calculate mass, we know the formula M is equal to rho multiplied by V. So our density is 7850 multiplied by 6.59 into 10 raised to minus 5. So our mass is 0.570 kg. Now next step is to calculate ball screw inertia. And to calculate ball screw inertia, we know the formula J is equal to 1 half mr square. Substitute the values in the formula, so we get J is equal to 1 by 2 multiplied by 0.517 multiplied by 0.008 square. So we get J is equal to 1.65 multiplied by 10 raised to minus 5 kg per meter square. And this is the inertia of rotating ball screw alone. Now next step is to calculate reflected load inertia. The moving mass travels linearly. Since the servo motor is rotate, so we must convert a linear inertia into an equivalent rotational inertia. And we know the formula to calculate a reflected load inertia. J is equal to ml square divided by 4 pi square, where J is reflected inertia, m is equal to moving mass, and L is equal to ball screw lead. Convert this 10 mm lead into a meter, so we get 0.01 meter. Substitute the values in the formula. J is equal to 15 multiplied by 0.01 square divided by 4 multiplied by pi square. So we get a reflected load inertia. J is equal to 3.80 into a 10 raised to minus 5 kg meter square. So after calculating reflected load inertia, we notice that the moving mass contributes more inertia than the ball screw inertia itself. So our total load inertia J is equal to ball screw inertia plus coupling inertia plus reflected load inertia. We have two values and we don't know a coupling inertia, and the coupling inertia is selected from manufacturer's catalog, and we are considering a coupling inertia 4.5 into a 10 raised to 6 for our design calculations. This value we have not assumed. This value comes from manufacturer's catalog. So substitute the values in the formula. We know the ball screw inertia is 1.65 into 10 raised to minus 5. Substitute the values in the formula. So we get a total inertia is 5.90 into a 10 raised to minus 5 kg per meter cube. And now it's time to calculate a servo rotor inertia. And every servo motor has its own inertia, and this value is published in the manufacturer's catalog. So we don't calculate it now. We will take this value later from manufacturer's catalog when we select a servo motor from the catalog. So we know the inertia ratio is equal to total load inertia divided by motor inertia, and we will calculate this inertia after selecting a specific servo motor from manufacturer's catalog. So in this video we have calculated the inertia of ball screw, the reflected load inertia of moving mass, and combine them with the coupling inertia to determine the total inertia acting on the servo motor. So in the next part we will select a servo motor from manufacturer's catalog and verify whether the motor is correctly matches with our fiber laser cutting machine Z-axis requirements. If you found this video helpful, like, share and subscribe the Machine Design Engineer YouTube channel and press the bell icon so you don't miss the next episode. Thanks for watching.